All right. In example 14, we're going to look at the left end and right end behavior of a rational function, 7x divided by 3x squared plus 2. We're going to use this problem for an additional check for understanding, and then we're going to talk a little bit more about the way the function behaves. So what I want you to do now is press pause, evaluate these two limits, and then come back when you're done. All right, now that you're back, limit as x goes to negative infinity of 7x divided by 3x squared plus 2. Okay, as x goes to negative infinity, the numerator goes to negative infinity. The denominator goes to positive infinity. The numerator goes to positive infinity at a faster rate than the denominator goes to negative infinity. So as a result, this quotient is going to 0 from below, we say, or from the negative side, because as x gets smaller and smaller, as we move leftward further and further on the x-axis, this quotient is going to become closer and closer to 0, but it's still going to have a negative value because the numerator is going to be negative and the denominator is going to be positive. So how do you know that? Just based on the fact that the numerator is linear with a positive coefficient and the denominator is quadratic with a positive coefficient. So a lot of that reasoning comes into knowing how y equals 7x behaves and how y equals 3x squared plus 2 behave, and then again the interaction between the two. Okay, we don't need to know what the graph of 7x divided by 3x squared plus 2 looks like in order to evaluate this limit. All right, the limit as x goes to positive infinity of 7x divided by 3x squared plus 2. As x goes to infinity, 7x goes to infinity, so the numerator goes to infinity, and the denominator goes to infinity. Remember, you cannot say that infinity divided by infinity is 1 because functions can go to infinity at different rates. Okay, in this case, the denominator goes to infinity at a faster rate than the numerator does because quadratic growth is more rapid than linear growth. So as a result, this limit is equal to 0 from the positive side or from above. Okay, so what this tells us in terms of behaviors of the graph, we know that this function has horizontally asymptotic behavior on both ends and that the equation for its horizontal asymptote is y equals 0. All right, we're going to write that down. All right, and that's on both ends. So you can't say that the horizontal asymptote is 0. That's just a number. You need an equation of a line. Now, what I did is I went into Desmos and I created a graph of this function so we could talk about how it behaves. Okay, we see this horizontally asymptotic behavior. So f of x equals 7x divided by 3x squared plus 2 has a horizontal asymptote of y equals 2. We just established that from the work that we did. This is an example of a function that crosses its horizontal asymptote, which sometimes throws some math analysis students into cognitive dissonance. And the reason for that is because they've never seen a function that crosses its horizontal asymptote, and they have a strong likelihood of having an incorrect definition of what a horizontal asymptote is. All right, when you first start looking at horizontal asymptotes, you have y equals 1 divided by x and y equals 1 divided by x squared. And those happen not to cross their horizontal asymptote. When you get into higher level math, then you start looking at functions that do cross their horizontal asymptote. So right here, you see that the graph crossed its horizontal asymptote. Now, I've had students who had a misunderstanding of what a horizontal asymptote was, and they'd take this graph right here and they'd erase that part and put a hole there. I'd say, what are you doing? They're like, oh, there has to be a hole there. I said, why does there have to be a hole there? And he said, well, because a function can't cross its asymptote. I said, no, that's not true. Function can cross its horizontal asymptote. Right? It just needs to approach it. So the The horizontal asymptote is a line that the graph approaches. Right? The but does not cross is not part of that deal. All right. We're going to explore this stuff in much greater detail next year in AP Calculus when we go through a unit called curve sketching, where we'll be able to analyze all the behaviors of this graph. So this graph has an x-intercept right here at the origin. The algebra supports that, and it's an example of a graph that can cross its horizontal asymptote. Right? You may not have been exposed to graphs that cross their horizontal asymptote before, but you have to remember that your experience with these things, regardless of how well you're doing in class, is limited because we're not even done with math analysis yet. Right? So you haven't been exposed to every situation that's out there. So remember, a function can cross its horizontal asymptote. Here we have an example thereof.